Academy for giving me this opportunity to present the research that we are doing for last few years in my group at TI for Hyderabad. And what I'm going to do is that I'm going to give you an overview of one of the problems that is actually being under progress in my group and which we are excited about. Just to do that, what I'm going to talk about is that briefly I will talk about the topic that we are interested in, which is basically called biomolecular recognitions. But this is basically a more generic topic which actually is quite omnipresent in the life and the matter. But the topic that we are specifically interested in is basically more biologically or biochemically relevant, which is basically called protein ligand binding. So if we try to really schematically draw the picture that we are really thinking about, so we have a protein which generally have a particular designated binding site, and for that particular binding site generally there will be some small molecule which we generally call it ligand, and generally they try to combine together and try to form a complex which is called protein ligand complex. So if you really think in terms of chemistry, one can actually think about a very straightforward reversible reaction where we have protein which is complex with ligand to form this particular thing, and this is important, this is a reversible reactions. So basically this binding and unbinding actually occurs in real time over the process of the time, and the relevance that we can actually talk about is two topics, which is basically the drug target recognitions for most of the drug discovery, which is quite popular, but we are not really going to talk about any medicinal chemistry here. Second point is that this is pretty much common in any numerous biochemical pathways, and this is just an example where you can see one drug which is basically called a kinase inhibitor, dasatinib, which is bound with the kinase in its bound pocket. So what we are actually interested in, which is might sound pretty naive, but from the perspective of our group, the question actually still I feel that is very interesting. The question is that let us say you have a small molecule like benzene here that we are going to talk about, and you have a protein which is basically supposed to recognize this two. So the question that we generally have is that how does this small molecule ligand actually try to find all the it diffuses around the protein and in the water, and finally gets in this particular thing in a precise locations and in a precise time. The question is that is it possible that you can actually atomistically look at this particular process in a computer, and is computation can be a tool of choice, which is that is basically the topic that you are interested in. This becomes more complex if you generally think about a particular protein cavity which is basically called solvent inaccessible, or you can call buried cavity. We are going to talk about a couple of those examples today, but the question is that we are trying to figure out whether the computer can be a tool of choice, because generally from experiment definitely one can calculate the macroscopic quantities, but looking at the kinetic pathways are generally complicated in that sense that the atomistic precision that you are generally looking for in these things are generally not present in most of the experimental tools, and that is why I think we try to see whether modeling can actually be a useful tool in these particular cases. But the question is, has this particular approach been there for a while or not? So this is to basically assess this particular thing. I have basically just trying to schematically plot two things. On this one axis, you have something called computational expense. That means whether you need large good computers, and the second here you actually have the accuracy, which is on the y-axis. So if you try to plot this particular thing, so what we will say is that the most popular technique, which is pretty much prevalent in the community, which is called rigid body docking. So here what you do is that you have a small, you have a target which is basically the protein cavity. One try to sample the targets around with different kinds of candidate ligand and try to see whether it can fit in that particular target. And that is basically like you have a lock and you are trying to basically find a key, and basically you try to then form a complex. So the advantage is that it's basically computationally ultra fast. One can do it without much trouble. But the problem is that you are pretty much biased here, because you are only locating your all your energy in a particular location, which you are assuming that that is the location where your ligand is supposed to bind. Now the second approach, which is I can say that computationally is slightly more expensive. This is basically which is also quite present in literature, and you know that this is also relatively more accurate than this, where they try to look at the other options, where they try to see you have a ligand which is already bound here, so you know these particular bound locations, and then you try to do the other process, that is the whether you can use some artificial force and try to get these ligands out of this particular process. And if you think that this is a reversible process, maybe there is a chance that you can somehow infer that how this binding would have happened. So this is one of the advantages that people think that this is relatively faster to do, but the problem is that these are actually biased, and it depends how you are going to pull this ligand out. So there is this reaction coordinate that one need to really figure out, and most importantly, there is no assessment of the time scale that you are basically talking here, because whenever you are putting a bias, you are pretty much corrupting the time scale that you are interested in. So the question, and basically every computer simulation person's bucket list is that, is it possible that you can do the most straightforward one, where you have a small molecule ligand somewhere here? Is it possible that we can actually completely explore all the positions that this ligand can take, and finally can we finally get to this particular point when the ligand on its own finds this particular designated cavity? And one of the technique that one can think about is basically molecular dynamic simulations. The advantage that I'm going to tell you is that this actually is a Newtonian dynamics that is basically being followed here. So it is a very realistic process. One can actually, if you can do it, one can actually think about a proper time scale, and one can actually get atomistic precision things, but at the same time this is computationally expensive. So to give you an idea of what is computational expense, I am going to basically briefly show you what is actually molecular dynamics simulations. So basically molecular dynamics for this particular things, what I am doing is that I am trying to show one heavy object, let us say this green color thing, which is solvated in a box of water, and what we are trying to do is that we are trying to see how this heavy object is actually diffusing inside this box of water in presence of this thing. So the way you generally simulate this thing in molecular dynamics is that you start with these configurations, you say that how these molecules are interacting with each other based on some potential energy, and then simply use the Newtonian mechanics to solve how it is going to propagate over time with the time. So this is actually, if we believe that this process is classical and one can actually ignore the quantum mechanics perspective of this particular process, then the advantage is that we can actually provide atomistically precise account of the molecular process at real time. So that is basically the advantage. But the problem that actually happens is these processes are actually dependent significantly on the system size that we are interested in, and more importantly, the question is that can you actually now do the same thing when it comes to protein ligand binding dynamics in real time? That means can we go beyond this idea of in silico docking? The challenge actually is that more than the system size, generally this idea is there in these molecular dynamic simulations. The landscape of the free energy that you generally explore, it becomes more complex with the systems, and generally it is riddled with lots of bottlenecks and kinetic traps. So one, if you can try to look at this binding and unbinding dynamics over time in a computer, it becomes very difficult that you might get trapped in a particular locations, and it might take a long time to overcome that particular process. And in the meantime, maybe we do not have that computational resources which can actually do these things. And at the same time, the stochasticity is very prominent in these particular processes. So that is why the statistical significance is also needs to be really assessed. So with this particular point, then the question is that can we actually really overcome these time scale issues? So to do that, what the community is trying to do is that they are trying to use a very interesting technique. So far, we have done all our simulations in CPUs. That is that is basically the conventional way of doing the computers. But what recently we have started finding is that if you use the graphics processing unit, which is the GPU, which is basically called graphics card, which is to be generally very popular for most of the gamers for playing video games and all these things, people started finding that one can actually do quite a good computation if you can write a program called CUDA, and you can plug it together with CPU and GPU, and one can find that one can actually get a very large increase in the time scales. And this is one of the video game graphics card which is basically developed by some company called NVIDIA, and this is basically called GE4 GTX. This is pretty much a graphics card which is pretty common in the market, and one can actually get it. It is like a consumer level graphics card. So what we have done in TIFR Hyderabad is, so we have tried to use a very simple CPU architecture, and in each of these things we have just added this video game card in each of these machines, and then we have found that whether we can actually simulate the process of a complex system which is like protein ligand binding. So that is basically the thing I'm going to talk about today. So in our group, what we are trying to do, we are trying to use the atomistic molecular dynamics simulations approach. We are trying to couple these things with high performance computing, but then we use one particular algorithm which is called Markov state modeling to make sure that our result is statistically significant and whether we can actually infer the long time scale processes in our simulations. So in today's talk, what I'm going to do is that I'm going to talk about two systems which we have studied and which we are basically studied and which are basically very classic system of protein ligand binding system, but it involves buried cavity. So one of the system is basically called P4 lysozyme, which is basically binding with a small molecule called benzene. So this the black one is the benzene in this particular cartoon representation. But if you try to represent it in a space filling model, what you can see is that this particular benzene is pretty much invisible. So this is basically the classic case of example of a buried cavity. That means that once the benzene gets in there, you just cannot see it from the outside. So the question is that how does still can it go there, and it goes quite fast actually. This is another system which is actually more pharmaceutically more relevant. This is basically called cytochrome P450. This is a metalloenzyme, and in this particular enzyme you have a heme active sites, and one of the molecule that people generally study in experimentally is basically called camphor. And in this particular cases, you can also see that this camphor binds near the heme active sites, but at the same time, if you try to look at in a space filling representation, you cannot see it from outside. So this is basically like a site which even water cannot access. That is why it's called a buried cavity or solvent inaccessible cavity. So what we really wanted to show is that can we use the molecular dynamics simulations to see how does these small molecules actually accesses these two particular cases. So this actually resulted in two different projects in our group. So so better that I will just basically show you two of the simulation trajectories which actually will convince you that how this particular process is happening. So this is basically the first project that we basically did, where we have this small molecule benzene which is solvated in water, and you have this protein which is also fluctuating with time, and this is your active site. So what we can do is that we can just play a simulation trajectory. So what you can see is that in this particular case, this molecule is actually moving around in the water. Sometimes it touches around the protein, this benzene molecule. But what I will see is that if you basically run it long time, this particular simulation trajectory was about 3 microseconds, which you can see is that eventually this molecule will actually eventually find this active site in an atomistic precision. So this actually is one of the trajectories. We have tried it in multiple cases. In all cases, we could see this particular binding. This is one particular observation. The second project is basically even interesting in a different way. We will see the difference in soon. So here I am going to start our simulation trajectory from 2.6 microseconds. Before that, the ligand has been spent most of its time in water. So if you basically try to look at this particular movie, this is for camphor with the benzene. So what you will see is that unlike the previous case, here the ligand is spending a significant amount of time near this particular pocket, and what it is doing is that it is trying to induce a particular small opening in this particular protein cavity. And what we will see is that if you just wait long enough, which is already now about 4.2 microseconds, which is basically possible because you can do it in GPUs, and what you will see is that eventually if you wait long enough, this particular ligand actually generally gets inside and basically sits in this particular pocket without getting it out within the time. So the question is how good we are doing as far as the experimental validation is concerned. So the best way to check is that this system has been studied experimentally in a very accurate way. So what you can do is that there are crystallographic picture of this ligand which is already bound there. So what we are doing is that we are overlaying our simulated bound force, which is this white colored protein with this red colored bound force, which is from crystallographic picture. One cannot. So what we will see is that you cannot just distinguish these two. So these are basically pretty much showing that you can actually simulate the process in accuracy, which is almost angstrom level, which is coming from this RMST. So this is one of the systems which is the T4 lysozyme in benzene. For the other system also, which is P450. So what you will see is that if you try to overlay the crystallographic and our simulated pose after the ligand gets in there, you will see that these two structures are almost matching with each other. This is also near the binding pocket. If you try to look at the crystallographic pose and simulated pose, these two will be pretty much identical to each other. So this actually tells you that the simulation force field that is basically there in the parameters and the unbiasedness of the molecular dynamics simulations is accurately reproducing the crystallographic pose without without much error actually. So that is one good thing. Then the question is that what we are learning out of all these things. So what I'm going to do is that now we have the trajectory which is at our disposal, and what you can now do is that you can go back and you can look at our trajectory. So what I'm going to first show you, if we try to look at one of the system which is T4 lysozyme, we have run multiple trajectories. So one of these cases, if you try to look at snippets of the trajectory, so let us look at this particular trajectory where the simulation, the ligand is here, and this is helices are colored in a particular way. This is called helix 4 and this is called helix 6. What we'll see is that in this particular trajectory, the ligand is actually trying to approach the pocket from this particular side through helix 4 and helix 6. Now if you look at another trajectory, interestingly what we will see, the same ligand now is going to approach from helix 7 and helix 9. So this is basically called, you have basically multiple pathways that is basically present in this particular case of the simulations. The question is that then what is actually driving this particular process. So if we try to now look at one of the simulation trajectories, and if we try to investigate a bit more on this particular atomistic precision, what we see is that if we try to plot the ligand binding trajectory on this left y-axis, and if we try to compare this thing with the helix 7 and helix 9 opening, you will see that when the ligand was outside, the distance between the helix 7 and helix 9 was small. Once it basically all of a sudden you will see that the gate just opens up, snaps open, and then the ligand gets in here and it automatically closes, and that is what we generally see. So this is basically a situation we generally call conformational selections, where the ligand is basically waiting for this right time when this gate is opening, and the moment the gate opens, it finds the time right, it just gets in there. So that is one particular observation. The question is that, is it possible that we can actually now quantify these things in a more accurate way? Is it possible that we can actually say that how many pathways are actually possible in this particular case, and what is the contribution of each of these pathways? So what we generally use is that we use a technique called Markov-State model to quantitatively address these questions. So in Markov-State model, the idea is that we run many long trajectories and many short trajectories, and we discretize our trajectories into certain microstate based on the state to state transitions, and then we try to see that whether we can actually then finally tell the story instead of telling the entire trajectory but in a statistically significant but in a certain number of macro states. So this is what I'm going to show you. So if you try to combine your the entire result for T4 lysozyme, you can break this entire system into 4 macro states. MS0 is the state where you have all the ligands completely outside, where the ligand is completely outside. This is the MS3, which is the complete bound state. Then you have two other intermediate, which is called MS1 and MS2, which is near helix 7 and helix 4. What you will see is that most of the trajectory is actually basically getting through from MS0 through MS1 but MS3, but at the same time we do see there is significant transition which is happening from MS0 to MS3, which is direct conversion, and that is actually about 39%. So this is actually possible because we can now actually have a particular model which is statistical build model from Markov-State model, which can actually accurately tell what is actually going on. More importantly, if you try to look at the lifetime of this intermediate, which is 69 nanosecond and 742 nanosecond, these are very transient intermediate, which is very difficult for an experiment like NMR to track this kind of intermediate. So in that particular case, this particular process can at least give you an atomistic precision idea of what is actually going on. So this is basically one particular example where you have multiple pathways, a short-lived intermediate, which is leading to binding in T4 lysozyme. So I am not going to tell too much about the cytochrome P450, but we did the same thing for this particular problem. But what we found, to our surprise, unlike the other one, here we see that there is actually only one particular dominant pathway. And interestingly, you have a dominant pathway where you have an intermediate which is very long lived, about 2 microseconds, which is actually telling you that something else is going on here. So what is actually going on, if you really want to investigate, what we will see is that in this particular case, I'll just finish this particular work with one small movie where you will see that 2-phenyl alanine ring is basically acting as a gate, and this particular ligand is trying to just open this gate. So it is pretty much the opposite of the other one, where it is inducing a particular open gate so that it can just get inside this particular pocket. And what you will see is that once this particular hydrophobic gate opens up, the ligand actually gets in. So this is basically quite contrary to the other one, which is basically called induced feed. So this observation is actually quite accurate as far as the previous experimental data is concerned. So with this, I'll just conclude. So summary, what I wanted to show you is that one can use computer simulations using the framework of molecular dynamics simulations so you can actually elucidate the kinetic pathways in an accurate way. Thank you.